Hello everyone, my name is Parv Maheshwari and I am a rising senior at Indian Institute of Technology, Kharagpur, where I major in mathematics and computing. Today, I will be presenting my work learning vehicle dynamics through interactions for off-road driving, which was done as part of the Robotics Institute Summer Scholars Program at Carnegie Mellon University. Motivation of this project comes from the fact that in off-road navigation, robots often have to perform aggressive maneuvers to traverse difficult terrains. Not only this, but they are also required to adapt to the changing environments, including different terrains. These requirements call for a robust and adaptive vehicle model to accurately predict the motion of the robot, and such a vehicle model is achieved through system identification. We use the standard formulation of state space dynamics, which is used to predict the future change in state depending on the current observations and actions. As a common practice, we consider that both the front tires compulsorily have the same steering. Due to this, we can effectively combine the left pair and right pair into just one, which results in a model very similar to bicycle. Now, we consider a state space X, which consists of positional coordinates, yaw, linear velocity, steering angle of the vehicle. For actions, we provide the robot with target throttle and target steering angle. To use this state and action space, we use an augmented kinematic bicycle model. The major points of interest is that we express the linear acceleration of the vehicle considering the effect of throttle, engine braking and frictional force. These effects are expressed using KT, KB and KF respectively. We also model the rate of change in steering as a proportional gain with respect to the target steering. Here KD is the coefficient of proportional gain. Now the major question is, what are the value of these parameters? So to answer this question, we use system identification methods. Now in a general sense, aim of system identification is to find a set of parameters that best describe a given vehicle model for the given trajectory and conditions. To use this, we have used our vehicle model to roll out the effect of a sequence of actions depending on the initial state. We measure the accuracy of our vehicle models in terms of loss, which is calculated as an L2 norm between the ground truth and the predicted trajectory. We can categorize our approaches for system identification as either offline or online. While we explore our traditional offline approach, we evaluate our traditional online approach while proposing a novel architecture for learning-based online system identification. Now it is finally time to dive into our methodology. First off, we have our algorithm for offline variant of the traditional system identification. Here, the aim is to find a general set of parameters to best describe the vehicle model on the entire dataset. Since we use the entire dataset to calculate a loss, the performance of these parameters would not be the most optimal for almost any individual trajectory, but would be good enough for most of them. The second approach is using the online variant of the traditional system identification. For all the online approaches, the aim is to find a specific set of parameters in real time to best describe the vehicle model for a particular trajectory at time t. A note here is that we warm set the optimizations with the output of the offline approach and not like default random values as used in offline approach. So now we already have both the offline and online variants of the traditional system identification. So why do we need anything else? It turns out that we need another online approach as the current online variant of the traditional approach suffers from the fact that it can only run a single epoch of optimization in real time, which is not at all good enough to improve the performance, and actually in most cases a single epoch over warm started parameters degrades the performance. Along with this, the traditional online approach is also restricted to be in reactive paradigm since it only uses a history of trajectory. Due to this, we would never be able to incorporate future information into the system identification. After realizing these issues, we tried a motivational experiment by combining the online and offline variants by running multiple optimization epochs over a particular trajectory warm started by the offline parameters. It turns out that this approach does result in more accurate parameters for that particular trajectory. You can see a clear-cut difference between the yellow and the blue trajectories. This approach would also solve the issue of the time required to predict the parameters in real time, as the neural network can predict at a much faster rate than the traditional online approach. With this motivation, we propose a novel neural architecture to perform online system identification by using data generated through offline system identification or individual trajectories. Once the ground truth labels have been extracted, we move on to the training of the neural network, where we first represent the history of odometry and steering wheel as trajectories in a vehicle's model state space. These trajectories are then passed through the wavenet encoder, which outputs an intermediate representation, which when combined with the current parameters are then passed through the multilayer perceptron to output individual Gaussian distributions for each parameters. The final parameters are then randomly sampled from these individual distributions. As it can be seen from the table, the learning-based online system identification outperforms both the other approaches, especially when all of the states are combined together. We can clearly see that even if the learning-based approach might not be most optimal always, it is usually better than the other approaches. The robustness of this learning approach can be increased by using a larger data set for the model to become robust to unseen scenarios also. For traditional online approach, as we said, the ability to run only a single epoch in real time results mostly in a downgrade of the performance rather than improvement when compared to the offline approach. Now moving on, we aim to integrate our system identification approaches with our existing navigation stack and test the same in navigational experiments on our ATV. We would also like to use the entire Tartan Drive dataset, which contains more than 5 hours of off-road driving. By using such an extensive dataset, we would improve the robustness of both the offline approach along with the learning-based approach. Future works would also focus on using additional input modalities like the forward-facing terrain maps in our learning-based online system identification. This would help us incorporate information about the future environment and would also allow us to shift the paradigm of the learning-based approach from a currently reactive paradigm to a more predictive one. At last, I would like to thank Dr. Winshin Wang, Dr. Sebastian Scherer and Samuel Trice for their immeasurable support and mentorship throughout the project. I'd also like to thank Rachel Burchin and Dr. John M. Dolan for coordinating this program. Thank you.